The concepts of iterated removal of dominated strategies or rationalizability build on very weak assumptions. The only thing we need to assume about agents' behavior is common knowledge of rationality. So using just this simple idea of common knowledge of rationality, we're actually able to say quite a bit for many games. But there's a trade-off here. Because we're making only this very simple assumption, there are some games where we're not going to be able to say much. Let's take an example. Suppose you're walking down a path, and there's another person walking in the opposite direction. It's not a terribly wide path, but there's enough room for two people to pass in opposite directions. However, you want to make sure you don't walk right into the person. So you need to walk either to the left or to the right. Let's say you both have your headphones on, and so you can't really speak to one another. You can't make much communication, but you just know that there's somebody there, and you're about to approach them. So you need to decide independently whether you should walk on the left side or the right side. If you both walk on your left, then you don't run into one another. One of you is going this way, the other is going this way. So if you both go on your left, then you pass one another. If you both walk on your right, then again you pass one another. However, if one of you goes to the left, you go to your left, they go to their right, then you're going to run into each other. Similarly, if they go to their left and you go to your right, then you're going to walk into one another. You both prefer not to run into the other person. So if you pass each other without bumping into one another, you get a payoff of 1. If you bump into one another, you both get a payoff of 0. Neither left nor right is dominated. It's not even weakly dominated. So none of the concepts that we've seen previously are going to be much help in figuring out what players should do here. What you do is going to depend on what you think the other person's going to do. So if I think the other guy's going to walk left, then I should also walk left. If I think the other guy's going to go on his right, then I should also go on my right. So my best response depends on what I think the other person's going to do. So where do these expectations come from? Well, these expectations come from a few different places. There are social norms. So in some countries we walk on the left, and everybody's expected to walk on the left. In other countries people walk on the right, and everybody's expected to walk on the right. There are sometimes laws. So if you thought about this instead of walking, let's say this was driving, in the UK the law says you have to drive on the left side of the road. Whereas here, the law says you have to drive on the right side of the road. You could have laws that tell you what to expect the other person to do. You could coordinate with the other player before you play the game. So perhaps before entering the trail to go for a walk, you might meet this player and say, hey, if we come across each other, we should both walk on the left. So you could have a coordination beforehand, so you both know what to expect the other person is going to do. Or you might have some experience playing this game. So if you played the same game many times with the same player, over time you realize this is what this person does, and you settle into a pattern of how to play against this person. Another example might be mediation. Perhaps there's a mediator, a referee if you will, who comes in and says, hey, look, there's a guy coming your way, you should walk to the left. I'm going to tell him to walk to the left as well. So there are all these different places where your expectation of what the other guy might do comes from. Now these expectations, remember, are what we call your beliefs. So what I expect you to do is my belief about the strategy that you're going to play. So once I know what the player's beliefs are, then we can actually get somewhere in solving this game. Remember, playing left is rationalized by the belief that the other guy is going to play left as well. Playing right is rationalized by the belief that the other guy is going to play right as well. So if I believe that you'll play left, I'm going to also play left. Similarly, if I believe that you're going to play right, then I'm also going to play right. Given that these expectations, or these beliefs, come about in the various ways that I described, so from these various social institutions, or from coordination, or experience, and so forth, it's somewhat reasonable to suppose that the expectations are actually going to reflect reality. Now, of course, this is a stronger assumption than common knowledge of rationality. Yet, it's not a terrible assumption to make. It's just saying that these beliefs are actually based in reality. So if we're playing this game repeatedly, then my beliefs are based on what I've observed you do in the past. Or they're based on the laws that regulate the way we play this game, and so forth. So either social institutions or history, these various things are going to inform our beliefs, and so we'll expect that these beliefs are actually going to reflect reality. So what do I mean by the beliefs reflecting reality? I mean that if player 1 is going to be playing strategy S1 and player 2 is going to be playing strategy S2, then player 1's belief, which is theta 2, is such that it puts probability of 1 on player 2 playing S2. Similarly, player 2's belief is that player 1 is going to play S1 with probability 1. If given these beliefs, both players are playing a best response, then we say that this strategy profile, S1 and S2, is a Nash equilibrium. In general, a Nash equilibrium is a strategy profile S such that for every player I, the strategy Si is a best response to what all the other players are doing at that profile, S minus I. In other words, utility that player I gets from playing Si, given that everybody else is playing S minus I, is at least what they would get from Si prime, given that everybody else plays S minus I, for all Si prime. How could we arrive at such a strategy profile S? Again, as we've seen before, it could be social norms. There could be a historical observation that you've seen other players play their respective strategies, and over time we settle into an equilibrium. It could be that we coordinated, and you can tell several other stories for how you might arrive at one of these types of profiles. In the game above, there are two Nash equilibria. The plural of equilibrium, by the way, is equilibria. And they are for both players to play left and for both players to play right. So if I believe that you're going to play left and I play left, and you believe I'm going to play left and you play left, that's what we call an equilibrium. Similarly, if you believe I'm going to play right and you play right, and I believe that you're going to play right and I also play right, that's an equilibrium. It means that neither of us has an incentive to deviate. So we're both playing mutual best responses. So the players are best responding to one another's strategies at a Nash equilibrium. There's a whole bunch of different games in figure 9.1 of the textbook where you can see what the Nash equilibria are. One thing you'll notice there, however, is that the only games in that table, in that figure, that have a single Nash equilibrium are those games that we could have solved with rationalizability, where there was a unique profile of rationalizable strategies. So you might wonder, wait, does that mean that whenever there's a unique Nash equilibrium that we would be able to solve the game using rationalizability? And that's not true. So let me give you another game where there's a unique Nash equilibrium, but rationalizability wouldn't help you. Have a look at this game here. Player 1 has strategies A, B, and C. Player 2 has strategies X, Y, and Z. None of A, B, and C is strictly dominated, or even weakly dominated for that matter. None of X, Y, or Z is dominated either. Let's make sure. Let's look at B. B has a strictly positive utility for player 1 when player 2 plays Y, and 0 otherwise. A gives you a positive payoff when player 2 plays X, and 0 otherwise. And C gives you a positive payoff when player 2 plays Z, and 0 otherwise. So none of these dominate one another. Similarly for player 2. What are the Nash equilibria here? What's the best response of player 1 if player 2 plays X? The best response would be to play A. So I'll just underline the payoff there. If player 2 plays Y, the best response is B. If player 2 plays Z, the best response is C. Now let's look at player 2's best responses. If player 1 plays A, the best response is Z. Player 1 plays B, best response is Y. Player 1 plays C, the best response is X. So the only strategy profile that consists of mutual best responses is BY. So just for some practice, let's look at yet another game. Let's look at this variation of the game we were looking at earlier where the players were walking down a path towards each other. Now, not only do they not want to run into each other, but let's suppose they prefer to walk to their left and pass each other so that the other person is on their right so that they can shake hands. So they both prefer that they don't run into each other and that they don't run into each other while walking to the left. So left is the best outcome. They both get a utility of 1 for just not running into the other person. They get 1 extra utility unit for also being able to shake the other person's hand. What are the Nash equilibria of this game? Just like before, there's still two Nash equilibria. It's still a Nash equilibrium for both players to walk on the left. If player 2 walks on his left, then the best response of player 1 is also to walk on his left. Why? Because if he walks on his left, he gets a payoff of 2, while switching to the right is going to give him a payoff of 0. On the other hand, if player 1 walks on his left, player 2's payoff from walking to his left is 2, while his payoff from walking to the right is 0. So walking on the left is a best response to player 1 walking on his left. So it's clear to see that both players walking on their left is a Nash equilibrium. However, there's one more Nash equilibrium, both players walking on the right. If player 1 walks on his right, player 2, by walking on his right, gets a payoff of 1. By switching to left, gets a payoff of 0. Since 0 is less than 1, right is a best response to right. Similarly, if player 2 is going to walk on his right, then player 1 is choosing between walking left and walking right. Walking right gives him a payoff of 1, walking left gives him a payoff of 0, so walking to the right is a best response. So right is a best response to right. So both players walking on their right would mean that they were mutually best responding. Though we have both of these equilibria, left-left and right-right, they both prefer left-left to right-right. Yet right-right could be a possible outcome. This is yet another example where the equilibrium outcome, the outcome of a non-cooperative game, could be Pareto inefficient. The outcome left-left, where both players get 2, makes everybody better off compared to the outcome right-right. Nonetheless, it is a plausible outcome that they would both play right. So even for games like this one, where there is no competition between the two, there are some games, like what we call zero-sum games, where one player's gain is another player's loss. This is not one of those games. Here, their gains are exactly the same. Either they both get 2, or they both get 1, or they both get 0. So their fates are tied together. Yet we see that the outcome in an equilibrium could be Pareto inefficient. So this is another example where when players respond to individual incentives, the outcome could end up being Pareto inefficient. Speaking of Pareto inefficient outcomes, if you recall the partnership game that we had seen, the effort levels that the two partners put in were inefficient levels. And we saw that the process of iterated removal of dominated strategies led to a unique profile of strategies. That unique profile of strategies has to be a Nash equilibrium. So let's see how you would have solved for that. Let's see how you would have solved for the unique Nash equilibrium without going through the process of iterated removal of dominated strategies. Remember that we solved for the best response function for both of the players. The best response function for player 1 was if the other firm chooses effort level Y, then you produce 1 plus C times Y. The best response of firm 2 was if the first firm produces effort level X, then put in effort level 1 plus C times X. Now let's suppose that X star and Y star form a Nash equilibrium. What do we know about X star and Y star if they're a Nash equilibrium? Well, we know that X star is a best response to Y star and Y star is a best response to X star. So this just says X star is among the best responses for player 1 to Y star, and Y star is among the best responses for player 2 to X star. But this means that X star has to be equal to 1 plus C times Y star, and Y star has to be equal to 1 plus C times X star. Let's call this equation 1, call this equation 2. If we substitute 2 into 1 and solve for X star, we find that X star is 1 plus C times 1 plus C times X star. That's 1 plus C squared times X star. So X star minus C squared times X star equals 1 plus C. That means X star times 1 minus C squared equals 1 plus C, but 1 minus C squared is 1 minus C times 1 plus C. So again, we can write that as X star equals 1 plus C divided by 1 minus C squared is 1 plus C times 1 minus C. 1 plus C's cancel, so we get 1 over 1 minus C. And substituting this back into 2, we get Y star is also equal to 1 over 1 minus C. So the Nash equilibrium is 1 over 1 minus C, 1 over 1 minus C. The same profile of strategies that survived iterated removal of dominated strategies.